Hi, everybody. Welcome to the Seal Connect Classroom webinar series. We're happy to have you here, and we appreciate you joining us today. We would like to welcome you and give everyone time to get into our webinar because some people do come in a little bit later. So while we're waiting to get started, Chris, hello. Thanks for joining us today and presenting.
Hey, thank you.
Of course, we want to give people time to get in, like I just said, so I'm repeating myself, and wanted to ask you a question. So tell us what the strangest or most enlightening application is that you've ever encountered, or something that you think is very interesting to share with everyone.
Okay. Well, I think with lubrication, as you travel around and you see a lot of creative ways for people to install vents and breathers and connect multiple machines together, there's uh, uh, people are very creative with oil cans and making oil cans out of normal household uh, containers and such. So cans and funnels. But I think probably the strangest application, we were looking at a pump in a mining application, and it was a temperature issue. And we discovered that they had decided, the maintenance technicians had decided to move from a 68 ISO 68 oil to a 220. And what that basically means is that 68 is like comparing water to syrup, and so that was causing the high temperature. And I think what's interesting or weird about that is they had a pretty interesting idea of what they were trying to accomplish. Being in a mining application, really dirty, they were thinking that the thicker oil would help coat and protect the machine. And so uh, what's weird about that is that they had a vent that was open just to the environment, and they would shut the machine down. It would cycle on and off, and so they were pulling in the dust and moisture and such. So the temperature issue was coming from the thicker oil, just trying to drive a bearing through oil. It's kind of like running in waist deep water at the beach. So it's just more energy, more temperature. Ultimately, we put a breather on it and was able to seal up the machine. But just interesting ways, creative ways that people apply lubrication. I think that's the one that comes to mind.
Awesome. Thanks. Excuse me. Thank you so much for sharing that with us. And we're going to go ahead and get started. And before we before we go into the actual presentation, we want to give you some housekeeping info. Seal Connect Classroom is a webinar series that aims to help you solve your problems and give you information that can help you with your equipment, with your team, with your reliability issues. You know, we're going to cover seals a lot, but we will also be having other experts outside of SEPCO, and just really, want to answer your questions. So if you have ideas for webinars, please send them to me. My email address is usually with the emails that we send out, and we will be happy to listen to what your ideas are. You can join the chat on social media with the hashtag SealConnect. You can ask questions in the Q&A section on the right-hand panel. So anytime during the webinar, if you have a question, ask it, and we're going to try to save some time at the end to answer those questions. If we don't get all of them answered, we will post a blog to answer them. The downloads on they're not called downloads, they are called something else, but there is a handout section, that's what it's called. On the right hand side, we do have a handout there, and it is an infographic on how to decrease oil changes. So if you would like to download that infographic, feel free to do so. The slides will be available for download, not in the resources section, but when we send you the email with the recorded webinar. So we are recording it, and within 24 hours of us finishing the webinar, we will send you the recording and the slides so that you can view it again or share it with your team at a later date. And with all that said, again, if you have questions, remember to put them in the question section. We have someone monitoring that, and we'll get to those at the end. And I'm going to turn it over to Chris Tyndall. He's going to tell you a little bit about himself and then get started with the webinar.
All right. Thank you, Lori. I guess first off, I feel like Ricky Bobby. I'm holding my hands because don't know what to do with my hands. So I talk with my hands. So if I start doing that, just bear with me. I think looking at the bio here, I've been in maintenance and reliability for going on 24 years. Prior to that, I was in construction and installing equipment, commissioning machines, and so had I think uh, I think along the way I've learned, it's not only what you know, but who you know. And, just looking at 24 years, I don't know how I got here. It was just yesterday. But I've had an opportunity to work with a lot of amazing people and just pioneers in reliability. And a lot of these guys that were the 20, 30-year guys when I started, they're still out there sharing what they've learned. And I think that's the important part of this reliability community, is just giving back and sharing what we know and what we've learned, our experiences, and learning from one another. So I'm glad that you guys are joining us today. I'm happy to be here. So our agenda, I guess our topic is understanding how our lube practices really impact reliability. And I want you to stop and think about your plant. Make this personal. Think about your plant and your equipment, how important bearings are to your process, because each process, each plant is a little bit different, but machines are the same. The bearings are the heart of our equipment. They carry the load, literally, and the lubricant that is the lifeblood of the bearing. So, bearings aren't typically assets; they're components, and they're disposable items, but they're extremely important. And the lubricant is also a subcomponent. Has a very critical impact to reliability of our equipment. So, we're going to talk about why protecting the bearing is important. We'll discuss lubrication and sources of contamination, why they should be eliminated, how to control them, and it's important to understand how to handle new oil, how to handle lubricants in general, from being new to making their way to our machines. And we'll discuss wear modes, how to identify them in real time, and understand what's going on in our equipment so that we can make changes to how we handle our lubricants and handle contaminants. And then we'll talk about technology, seals and breathers and filtration, just the different technologies that can affect and protect our equipment, our lubricants. All right, before we jump into that, we have a poll to get everyone thinking again. Lori, would you launch the first poll?
Of course, give me 1 second. All right, everyone should be seeing the poll now, and we're going to wait a few seconds, 30 or so, to let you guys vote on, we'll vote, answer this question. I guess it is kind of like voting, but we will, once we've got about 50 to 60% of everyone who has made a choice, we will close the poll. All right. So I'm going to share the results.
All right.
And the overwhelming favorite answer is 85% say lubrication, and the other 15% say improper storage and handling. None of the other answers got any votes. So lubrication overwhelmingly the number one answer from our attendees.
Okay. That's expected. I think lubricants. When you look at the poll, one way to answer that would be the most important uh, factor is the one that you're struggling with. It's basically a chain, and as we talk about bearings, it's there's a chain of custody from design and quality, storage and handling, how we install them, the equipment condition, the uh, having proper alignment and balance and proper torquing and for our fasteners. But lubricants, that takes it's a whole nother realm with the same thing. And when you look at the first, everyone has a part to play, from engineering to purchasing to warehouses to maintenance and operation. And the funny thing about lubricants, everybody from engineering and purchasing to how we handle it and how we maintain the lubricants. It's a chain of custody across the entire organization. So I think lubricants are a critical factor that we have to consider. So thanks for that. Um, so let's jump into this. We want to understand why bearing protection is important. So let's go back to the source. Let's see what bearing manufacturers have to say about this. And SKF is one that's done a study on this topic. In fact, it's estimated that roughly 10 million bearings are manufactured every year, and SKF says that only 10% of those bearings reach their design life. Um, just what is the first question you might ask is, what is design life, and how do they determine that? The L10 life is calculated by a standard. It's basically looking at lab environment for classifying bearings. They look at how many millions of revolutions a bearing will turn before failure, and they classify the bearing type by the point where 90% pass and 10% are failing. And so that is determining what the life expectancy should be. But they're saying that only 10% ever reach that. And what's interesting about this study is that they say more than half of the failures are due to the lubricant, contaminants, water, and particulates getting into the lubrication system and breaking down the lubricant and ultimately causing bearing failure. So the next question would be, how did they come up with this? Where do these figures come from? So SKF, since 1907, they've been manufacturing bearings, and they've been looking at failed bearings, and they, along with other bearing manufacturers and reliability guys along the way, have determined that you can look at a failed part, and from wear pattern analysis, you can see whether the failure was caused by misalignment, whether it was an overload or underload, erosion, corrosion, fatigue, overload kind of things. So over the last 100 years, they've compiled a lot of data and looking at real parts. So the next slide, I think most everyone's probably seen posters. There's an ISO standard that classifies how to evaluate bearing failures and how to look at wear patterns and determine the root cause, the failure mode. And so it's real clear when you look at a failed part, you can determine whether it was contamination, whether it was a misalignment or other cause of failure. So SKF is one source to look at, but they're saying that more than half of the bearing problems or the problems with the bearings they manufacture comes from the lubricant. So um, let's look at what lubricant manufacturers say about this. These studies, SKF determined that 75% of bearing failures can happen, uh, in regards to water contamination, can happen before the lubricants actually, before the water is visible. We know that, it's commonly said that water and oil does not mix. That's somewhat true, but not exactly. There's a saturation point with oil that before the water and the oil begins to separate. And depending on the viscosity and the type of oil will determine what that point is. But this is a good visual representation. So this slide is something you can refer back to. And basically looking from the left to the right with those samples, you can see clean oil that has uh, no trace or just trace amounts of water in the lubricant at 50 ppm or 0.05. It starts to become hazy. You can start seeing that the clarity is affected. What's important is that at 0.1%, at 100 ppm, is the point that they're saying 75% of the bearing life can be cut, it can be lost. And so as you move along to 0.25 all the way to 1,000 ppm, that 1.0%, that's the point when you start seeing water begin to separate in some oils, and even up as much as 2,000. So I think the next slide also goes along well with this. This is, again, for your reference to spend some time looking at this and determining, this was Exxon Mobil study. And they were looking at 2,500. If you look at the chart to the left, the 2,500 is a point where you have separated water in most oils. And so if you walk out to your equipment and you're able to take a sample and the water separates out, you're somewhere above 1,000, 2,500 ppm. And so this is a life extension table. So they determined that moving that back down to 200 ppm will increase the life of the oil, the lubricant, by a factor of 4. So directly impacts the life of the bearing, directly impacts the life of the lubricant. We know water and oil is not good. We wouldn't intentionally mix the two, but it happens. It happens in our processes. It happens by the way that we handle our lubricants coming in, how they're stored, how the machine is sealed in the field. And so this table is just a good reference. It shows you, again, the table to the right is giving you an indication of the appearance of the oil. So that gives you a visual. Another thing to point out is you can do a crackle test, which oil and water in the oil will begin to crackle under, if you put it on a hot plate, it'll begin to, the water will start to crackle and pop at about 200. So and then above that, it's of course becomes more apparent. But so visual, there's other quick field tests that can be done, and then there's laboratory tests. So we know that's a problem, but that's manufacturers. The bearing manufacturer says it's the lubricant. The lubricant says, hey, it's the contaminants. Yeah, this is a problem. But we have a couple of other studies. I mean, we could go on for days looking at different studies. I mean, this one was one that was done in Canada by the Society of Lubrication or Tribology and Lubrication Engineers and the NRCC, the Research Center of Canada. They looked at 3,700 failures across multiple industries. They also determined that 82% of mechanical failures were due to particle contamination. SKF also agreed in their study. They say that while we looked at cumulative results, SKF is saying that when you compare that to different industries, it will vary. The cause of failure being contaminant misalignment, installation, handling. But you can see they're all a problem. Mining, forestry, pulp and paper, electrical, they all are impacted financially. So they determined $5 billion was lost annually due to lubrication issues. So the next slide is not only, this is another study. This was Great Britain. There were similar studies done by Peter Joyce, Germany, Japan, China, and Canada. This was done back in 1966, and they determined that there was $1 trillion lost in Great Britain due to lubrication issues. It was 200 billion back in 1966. So adjusting that for today's rates, we're talking $1 trillion. And they said that lubrication failures were the leading cause. So the last study we'll look at is just one done here in the U.S. By MIT, and they determined that across our industries that we lose about $240 billion due to lubrication issues. And they said that, again, they agreed with SKF. Lubrication accounts for 40 to 50% of machine failures. They said that 70% of machine failures were due to surface degradation. Breaking that down, they determined mechanical wear to be 2/3 of that, and 1/3 caused by surface corrosion. The interesting thing is mechanical wear and surface corrosion, those are all functions that are prevented, or failure modes that are prevented by the lubricant. So when the lubricant fails, that's the result. So what do we do with these kind of numbers? What do we do with that? The next slide, I think we go into another poll. Up to this point, we've talked about post-mortem failures, looking at failed parts. We're going to transition after this poll into what can we do today. And Lori, would you launch the next poll?
I am launching it now, and as last time, we'll give you about 30 seconds to 60 seconds to answer. And we hope to have at least 60% of folks respond if possible. And we are close to that number. All right, we'll close the poll, and I'm going to share the results. So it is important that we ask this. 67% are not familiar, 27% somewhat, and only 7% are familiar. So hopefully this information you're about to share will be helpful to everyone. I'm going to hide the results, and we will go to the next slide.
All right. So again, what we've talked about so far is post-mortem, looking at failed bearings to determine forensically how they failed. And it's a very scientific process. It's repeatable. It's very objective, and it helps us to classify and understand what's happening again post-mortem, so that we can come back in and make adjustments. But we really need to understand our current condition and be able to measure the opportunity. We know there's big financial opportunities, so we need to know what the enemy looks like. And contamination is our biggest enemy, our biggest opportunity. So this slide is just a visual representation. And what I want to point out here is that if you center in on the green dot, that's 40 microns. That's representing the smallest particle that we can typically see with our eyes without any assistance, magnification. That if you wanted to try to understand what 40 microns looks like, take a fine ink pen and a clean white sheet of paper and try to make the smallest dot that you can make on that sheet of paper and still see it, and that is roughly 40 microns. So the smallest one you can keep trying, and that is when it's just visible and not visible, that's about 40 micron. Um, and then all the way up to, if we went and we took a grain of sand, you're typically in the 100 micron range. Human hair is somewhere between that 70 to 100 micron, uh, roughly. So just the cross section of a human hair. So that's just, you know, in relation to particle size. Here's what's important. Uh, the ones that are in the, oh, I'm sorry, Lori, can you go back? What's important here is looking at the clearances in the machine. Um, as we get down below 40 micron, they're not visible. So when you hold up a sample of oil and you look at it and it looks clear and there's not any particles, the particles that you can't see, that's what is really damaging your equipment. Those larger particles, they typically don't fit into the bearing clearances. They settle out. They have more density, more weight. They settle into the sump and they're swept out of the way. Now they can break down. They can get into other clearances and start to break down. So you definitely don't want to have sand or any other, you know, 70, 50, 40 micron particles. But the stuff that gets down into the clearances of the bearings, those are the ones that are really damaging. So the next slide is showing, typically I'm just trying to show you you know, what 1 milliliter of oil might look like. So if we took a sample and we looked at it and everything was clear and we could see roughly 3 particles floating around in there, you know, that may be considered good. But in this case, there's hundreds of other particles. Those are the ones that are floating around in the lubricant, silica, dust, and silt, and things that are going to damage our bearings. That's what's showing up in the postmortem reports. That when you look at the failures, you're seeing the indentations in the raceways due to these small particles. So the next slide is a reference. So this is just giving you an idea. There's a lot of these online. This is just a reference of machine clearances. You know, valves, when we talk about servo and proportional, directional valves and hydraulic systems, those are things that if there's contaminants, we know, we've known for a long time that they don't last long, that those clearances, any kind of contaminants in hydraulic oils cause quick failures, but all the way down to roller bearings, gears, journal bearings, the clearances vary, and so the particles and what we need to how we need to treat those particles changes based on the machine. So it's all about, just like with the water, how much is too much. Water, you know, is always going to be in oil unless you have it dried. How much is too much when we talk about particles? So let's dive a little deeper into that. The next slide is, how do we count, or how do we measure what's in our oil? What's going on with these particles that we can't see, this hidden enemy? You know, visual is one way to do it. The bottom of this slide is just showing you under magnification what various samples may look like, you know, progressing from good to bad to worse. And so under magnification, you can look at that and we can make a comparison visually using magnification. Now, how do we quantify that? So if someone was to show you these samples, down at the below that, you see an ISO code 181613. All right, how does that, what does that mean? How do we quantify? If you were showing these 5 patches, we could say what's good, what's bad, okay? But how do we measure whether we're getting better and make that trendable? There's a couple other methods. One is a pore blockage method, and so if you have dirty fluid, something that's it would just basically, you're passing the lubricant through a series of filters or screens that capture particles from largest to smallest, and so it looks at the pressure decay, the pressure drop across each one of the screens, and then from there we can calculate an amount of contaminants in that size range. So one size of the screen may capture all the particles that are 14 micron and greater, the next one 6 micron, the next one 4 micron, for instance. And then there's photocell laser methods. This is using a laser or a light source to look at the reflections of or the shadows being cast by particles, and from that you can measure size and even shape. Some of the instruments today are very sophisticated, and they can even tell you size, not only size but shape of the particles, and whether they're sliding, cutting, spalling, different things there. But just for reference, we're not going to dive too deep into this, but just to understand that this is a log type scale. So when you look at the ISO codes, the 4, 6, and 14, those are particle sizes, which we just looked at in the previous slides. And you're trying to count being able to compress a large amount of data range into a usable number and a reference chart. And so that's why when you start on the right-hand side, there's 55 particles at 14 microns. Or I'm sorry, we're going to start with 4 micron. We're going to look at all the particles that are in 1 milliliter of oil, and we counted 1,752 particles at 4 micron. Then from there, we're counting how many of those particles are larger than 6 micron. And so out of that 1,752 particles, there were 517 greater than 6 micron. And then when you moved to 14 micron, it dropped down to only 55 particles in the oil and the fluid that were greater than 14. So that's how this standard works. When you look at the table, it gives you a range that's something that's repeatable. You can look at, in this case, 55 particles drops in between 40 and 80. One thing you'll notice that each one of the numbers, it doubles. So you have 20 to 40, 40 to 80, 80 to 160, and so forth. So it's a doubling factor to give you a range, but it gives you a number, that 13, 16, 18, or 18, 16, 13 is how it'd be reported. So 1,700 particles fall in between 1,300 and 2,500. So it's a useful way to measure contaminants in real time. So we can pull an oil sample and we can know where we're at, and ultimately from there we need to determine what that means, how much is too much. So the next slide is going to show another poll, and this Lori, if you'll launch this poll.
I will. There we go.
Yep, we want to know if you filter new oil before putting into the equipment.
And again, we will give everyone time to answer who wants to. And we appreciate y'all doing these polls for us. This will be our last poll, so thank you for giving us your feedback. All right, I'm going to close the poll now. And of those that answered, we had 73% said no and 27% said yes. So almost a quarter of our attendees do not filter new oil. So I'm going to hide these results, and Chris,
Right,
we'll go to the next slide.
Okay, so let's look at that. New oil is for a hydraulic system. This is another ISO reference chart showing a couple of visuals of what that looks like in under magnification. For a hydraulic system, the ISO standard is a 151411, which is very clean. When you look at a 15 in the chart, a 15 is 160 to 320 particles. So that's what you're looking at as total number of particles greater than 4 micron. And then of course that drops down to at the 14 micron, you don't want anything, 10 to 20 particles in the lubricant. What's interesting is when you start looking at a new barrel that comes in, those are going to be up there in the high 20s. So you're going to have 22, 23, 21. I mean, you're talking, somewhere between 20 and 40,000. It's not uncommon to see even more than 40,000, sometimes up to 80,000 particles floating around in that barrel. And so the idea is the next from the top left to right, that's new oil delivered in a tanker. Why is that different? Well, when it's offloaded, it typically passes through a filter and before going into your storage tank, and so just dropping down from a 22 to a 19 is significant. I mean, we're talking it could be 40,000 particles all the way down to a 19, which is 2,500 particles. So you can see a clear difference in total particles. And then if it's in a sealed mini container, those are typically, again, filled into those containers and through filtration and polished up and all the way down to even a 17, which can be as low as 640 total particles. So that's a lot. It's still not where we need to be with a 15, but you can see that new oil is certainly not clean oil. It's not intended to be, and it can be, but there's a lot of money that goes into to buying pre-filtered oil, and it's just easy enough to do it ourselves. So the next slide, we're talking about a hydraulic system. And this, I really like this. This is for your reference to spend some time with and just understand, what does this really mean? So yeah, there's particles. How much is too much? What does that, how does that impact my machine? We know SKF says it's killing half our bearings. But this chart is basically showing you filtration, and not all filters are the same. 25 micron nominal, 10 micron nominal, 10 micron absolute, 6 micron absolute, and 3 micron absolute. There's a lot more. I think we might do another one of these, really focusing in on filter selection and such. We're not going to spend a ton of time here, but I want you to understand there is a difference. There's difference in filter types, beta ratios, how they capture and eliminate particles varies. Not all filters are created the same. But in this chart, you're basically comparing it to sandbags. So it's very visual. You can see 4 pallets of sandbags. That's the equivalent to 136 50-pound bags of sand. And since we understand particles and how to count them, and we know that ISO 21 is 20,000 particles max, so it's somewhere, falling between 10 and 20. We're going to call it 20. 19 is the next line item at 10 micron. That is 5,000. So from 2,500 to 5,000. 16 would be 640. 14 would be 160 max. And then down to the bottom where you have 12, which is 20 to 40 max particles. So since we know how many particles are in there, and this is basically pulling from a reservoir, circulating it through a filter, through your hydraulic system or your pump or your whatever machine, that's the equivalent. So we know how many particles, and we're moving that at, say, 5 gallons per minute for a year's time. That amount of particulate moving through that at a constant would be the equivalent to moving 136 50-pound bags of sand at 25 microns. So you can see just by removal, it's worth doing. If it's in there, we need to get it out. If it's not in there, we need to keep it out. But going down to 3 micron filtration, and it can drop you from 136 down to just over a fourth of a sandbag. 6 micron gets you to 1 sandbag. So I would much rather have 1 sandbag per year passing through my hydraulic system. And so you can start to connect the dots and see how SKF's post-mortem stuff connects to what we do in real time. So great reference chart. Really like that one. So the problem with wear particles is more than just the particle. When you look at particles in your lubricant, these particles aren't invited to the party. The water, the particles, they're just not invited to the party. When they get in there, they create more particles. So The large 100 micron, 70 micron, 40 micron particle can break down into a bunch of little ones, and then those cause machine wear, which ultimately creates more particles. So now we're not just talking about silica, we're talking about metal. And so, yeah, the next slide is great. I want you to think for a minute. We looked at the SKF charts. We looked at all the failure wear modes for looking at failed parts. These are the jigsaw puzzle pieces. So there's a whole nother standard that introduces us to what's going on in our lubricant, because all of those pits and craters and holes and gouges, all of that we're seeing on our failed bearing, we can also see the accompanying piece that came out floating around in our lubricant. So they're all different sizes. I like this chart, something again as a reference. There's tons of these that you can dive into. There's actual ASTM and ISO standards for classifying these and understanding the causes. But it all comes down to particle size, which you can see in the middle in microns, all the way from 1100 microns down to 10. And where these particles typically show up, whether they're rubbing, cutting, dirt, sliding wear, fatigue, and we're going to dive into that a little bit more in the next slides. So it's a very scientific process. You can see, this is a general classification: erosion, corrosion, fatigue, overload, adhesion, surface fatigue. All of those show up as different shapes. And so the next couple of slides, we're just going to zoom in on that and just talk a little bit on a high level about what that looks like. Because we can take an oil sample and we can look under magnification. Again, there's technology out there where not only are you using laser to count the particles, but they can use lasers now to not only count, but to determine the shapes. So if it's plowing, gouging, cutting wear, it looks like something that came off of our machine lathes. If that's going on in your machine, that's abrasive wear. Abrasive wear comes in two forms. It's the 3-body abrasive wear or 2-body abrasive wear. The one we've talked about the most today is that 3-body. That's when you get a particle in there. The lubricant is trying to keep two metal surfaces apart, and now I've got something in the middle that's bridging that gap. And when that happens, there's gouging, cutting, and the scoring that shows up in your bearings. So the next slides are going to just show you surface fatigue, the pothole effect, that once something starts, it just, those are those failed parts, and that's, the particles that came out of there, the spalling, the pitting, the brunelling. Once there's a dent, once that roller ball bearing or spherical roller bearing, once it rolls over that particle and it creates that dent, that hard particle creates that dent into the raceway, as it continues to that pothole effect, to dump, you're going to end up with the subsurface cracking and ultimately spalling that shows up in your parts and shows up floating in your oil today. So that's surface fatigue. And then there's adhesion. That's when just the lubricant's not doing its job. One of the cool things about a lubricant, oil has this great property that when you increase the load and pressure on oil, the viscosity goes up. It becomes thicker. It even becomes like a solid. So it keeps that barrier away from those two parts as your gears are rotating and meshing together, and they're meshing in and out and sliding. That oil's doing its part to try to keep those separated. In some cases, there's hydrodynamic lubrication, there's boundary lubrication. We're not going to go too far into that, other than to know that oil is there to bridge the gap. Film strength keeps things separated. Water does not share that quality. So water in your oil, water's not compressible. It has no film strength to be able to keep those parts separated. So again, water in your oil reduces your film strength, causes problems like this with 2-body adhesiveness, where the two pieces actually touch, weld together, and then separate, causing pieces, to tear apart and create sliding. You see the striations and the sliding wear, that becomes evident. So then the last one is just talking about corrosion. Corrosion, fatigue, fretting, cavitation, iron oxides. All of these are super small particles, but they're telling us whether there's a chemical attack, whether there's, rust happening in the system. Can point to water, can point to acid, salt, bacteria. All of those things start showing up in the oil sample as very, very fine, low micron particles. And again, particles create particles. So that's it for this standard. There's actually the next slide is just pointing you to the ASTM standard that helps you to categorize these. It's actually simple to follow. You can there's looking at a wear shape, you can start asking the right questions and sizing and looking at whether it's spherical, whether it's sliding, platelets, whatever, chunks, and then it will direct you down to what the obvious cause or the wear mode is. So great technology. It's available today. We've talked about what a failed part looks like, what we should do about that. We can measure this in real time. We can measure how much water is in, how much particulate, what that's actually doing to the machine, because that's the next question. How much is too much? What is it actually doing to my machine? What are the machine clearances? And so this is just a basic awareness at this point to know that it is a problem. And so now let's talk about the solution. The path to lubrication reliability starts with selecting the right lubricant, making sure that it's the right viscosity. That's always rule number one. Viscosity is the most important thing. It needs to be able to handle the temperature range, and the viscosity needs to be able to maintain a constant for that range. So there's an index value that comes into that, but the lubricant is important. Having the right amount of lubricant. I think we talked about the changing of viscosity. Higher the speeds, typically the lower the viscosity. Higher the loads, higher the viscosity. It's again a process that's pretty straightforward on how to determine what's required, but having the right amount, the right quality of the lubricant, making sure that storage and handling, it's clean, doesn't have contaminants in it, and getting it to the right place, being able to transport it and not damage the lubricant and replace it when it is spent. So critical path, it requires everybody's to work together to maintain the right lubricant. The next slide is going to talk about what happens when we do all these things and we still have contamination issues. If contamination issues are is important to prevent, we spend a lot of time on maybe filtering oils. I see people using oil containers that are sealed, which is great. Moving away from the coffee cans or the repurposed bleach container, the open cans that are being used. People are using sealed containers now. We're using breathers. We're using better seals. What happens when we do all this and we're still getting contaminants in the lubricant? So it's important to remember we can get them out once they get in, but an ounce of prevention is worth a pound of cure. We want to prevent these contaminants from being able to get into the machine versus having to filter them out. So I want you to stop and think for a minute. How do we keep contaminants from entering the lubricant? There's, we're going to talk about seals, but I want you to think about your machine reservoir. We've filtered the oil. We've taken it to the machine. We've used clean filters or clean funnels and such to get the lubricant in. Maybe we even pumped it in using a filter cart. Once it's in the machine, what do we do next? Because the machine has a reservoir that has seals. and it has a breather. It has to be able to breathe, and we're going to talk some more about that. In the next slide, I think we have an example. One of the things, well, when you think about a breather, there's it's important to have a the right type of breather. If it's open to atmosphere and the machine is cycled out of service, open vents then become a pathway directly into the machine. As the hot machine is running, it's venting out, yeah, this is a great place to talk about that. There's when the machine's running, it's venting out, and you have heat and higher pressure inside of the machine. The air is traveling out. It's traveling out through your vents, through your breathers, through your seals. When the machine is shut down, the power in cools, the machine begins to cool, and everything reverses. Everything is now coming in through the breather, in through the seals. And the thing is, going back to the other slide, there's this is showing a compounding, non-contacting labyrinth seal. There's a lot of these out there. There's lip seals, there's contacting seals, there's compounding seals that have lip seals inside and contacting seals. There's I don't know, 50, 100 different types of seals. Breathers are important. Breathers, number one, have a good breather, a desiccant breather, a good filter breather, to help prevent contaminants getting in through the breather. Let the machine breathe good, clean air. When it's venting out, when it's running, hey, that's great. That's where those hook vents come from. But I'm sorry, Larry, can you go back one more time? The What I want to point out here is that the compounding seals, because the shafts that enter the machine, those dynamic seals, those are the things that wear out. And so breathers, especially desiccant breathers, they change color and they tell you when they're no longer functioning, and those should be changed out. But those are very visible. You can see what's going on. And by the way, if it's changing color, it's actually doing a good thing. You'd much rather the breather change color than the moisture get into your machine. There are ways to maybe move the breather and create a snorkel, get it away from maybe high steam areas or something like that. But breathers are good. Static seals are pretty easy. The dynamic seal is what gets us. And so as the contacting seals run on the shaft, they fret, and then that's what causes our problems. So what I wanted to point you to is this technology that's out there, using two pieces. So this is just a quick cutaway for your reference later, to show you have a static seal that's sitting in the housing, and you have a dynamic seal, which is the rotor, the expeller, that's spinning, being driven by O-rings. There's nothing contacting inside of these seals, so nothing's wearing, so their performance does not change. So again, in the next slide, that's where we talk about the energy balance. Where that's really going to matter is when these machines are cycled out of service. So where do contaminants come from? They can come from breathers. We can pour them in. If we're not pouring them in, are they coming from the breathers? If there's a static seal, maybe it's a large machine that has a reservoir and there's a lid. Bolt the lids down with a gasket. I mean, those things, those are the sources of these contaminants coming in that take out our bearings. Most static seals are easy to handle. And then dynamic seals, we can measure the performance of these. So if you're doing everything else right, you've got good clean lubricants going in, you got a good breather, you got good static seals, then your dynamic seal becomes the point to look at. So the next slide is showing you how these work. Again, I just cutaway. Well, this is also a cutaway. They're basically using the machine's energy, because when the machine is hot, it needs to vent. It needs to be able to breathe. These non-contacting labyrinths allow for the air to vent through the seal, and then it uses the machine's energy to expel any kind of contaminants whenever things are running. If you had something spraying out or washing down around your machine, it's able to, as the rotor is spinning with the shaft. I think the next slide shows just the expulsion rate. So there's the next slide is going to be how things work dynamically. Compound labyrinth seals will, as the outside rotor is spinning 360 degrees around the circumference of the seal, it's expelling contaminants. So anything trying to get in, you're adding energy to it, and you're allowing the machine to vent. The air is escaping through the seal and it's pushing everything out. So dynamically, that's how they work. Now, statically is the part that gets most people. Statically, if you have a contacting seal, as that seal runs for some period of time, as it's contacting, those clearances begin to open up, and so the performance changes. And we forget that. We forget that when we're doing all of this and we go out and we still have particulate and moisture in our machine, a lot of that's coming in from the static system. You know, we focus a lot on the dynamic things when things are running, but statically, when the machine's cooling down, that's when it gets contaminants can get pulled in. What a compounding labyrinth does, in this case, you have a vertically mounted labyrinth, and it sits outside of the machine. So it sits outside of the housing. So as any kind of contaminants, as the machine's cooling down and it's pulling these vapors across, you got the vapors moving from high pressure to low pressure as it's cooling down. At some point, it will meet an equilibrium. It will balance out and it will stop. The energy transfer will stop. But during that time, the labyrinth allows for you to break down the contaminant. We're using in these types of designs, they use O-rings, non-contacting O-rings that are just throttling the exchange and breaking down those pressures, and then it just drains outside in the same manner that it was expelling. So it, at this point, instead of 360, it just drains down to the 6 o'clock position and drains outside of the machine. So the particles and the moisture does not get in. So and that is how that works. So we'll go into a time of to answer some questions and open that up. Thank you for your time.
Hey, Chris, thanks so much for a great presentation. I am going to take 1 second and pull up, I know everyone just saw that, any questions we might have. So we still have, I think, like a couple minutes. So if you have a question, type it in. If we don't answer it now, we will post a blog and make sure you get the link to it so that you can ask your questions. And before I ask this first question, I do want to say that our next webinar will be May 13th. That is a Thursday, and it will be at 11 a.m. Central. And we will be discussing sealing dry powders and slurries with an air seal technology. And we'll discuss some case studies and talk about that technology and how it can maybe solve some problems for you. Chris, we probably have time for one question. So let me ask you this.
Okay.
Do lubrication companies usually recommend that you filter new oil, since so many people don't do that? I just wanted to know if they typically recommend that you filter it.
They actually do. It's
Okay.
something that I think most people don't realize. We bring in lubricants, and it's just expected. The barrels that come in, the manufacturers would 100% agree that they need to be filtered prior to use. That and they will filter it for you. I mean, there's a charge for that, but again, it's one of those storage and handling things. It's best to bring it in and do your own filtering, either into the top off container that you're about to use or into the machine. So.
Okay. Well, again, Chris, thank you so much. Thanks to everyone who joined us. Sometime tomorrow, you'll get the recording, you'll get the slide deck. And if you think of any questions in the meantime, you see all of Chris Tyndall's contact information. And we just thank you so much for joining us today. And we hope you'll join us in May for our next webinar. Again, thanks, and have a great Tuesday, everybody. Thanks.
Thank you.